Hi there, this is the first in two parts. So I'm going to do 20 questions altogether, multiple choice, wave and oscillations. Obviously with full walkthrough solutions. So what I'll do first of all is show you the questions, then share with you the mark scheme, and then do a full walkthrough solutions for the first 10 questions. And if you need to watch any of them, you can watch them. Hopefully you'll find it useful. So I'll do the questions now. So this is number 1. Remember just to pause, attempt the question. The next question will show up in a few seconds. And there's the mark scheme if you want to check your work. And then what I'll do now is go back and go through all of the questions and show you how to get these answers. So this first one's pretty straightforward. We need to figure out the wavelength. So just make it so that don't move. So we'll just use V equals F lambda. The wavelength is the wave speed divided by the frequency, so it's 1.5 times 10 to the power 3 divided by the frequency 8 kilohertz, so that's 8,000 hertz, which is 0.1875, which means people might go for A. It's a distractor answer. Let's get rid of that. It's 12 complete oscillations, so you need to get that 0.1875 and times it by 12, as it wants the length of the full pulse, so it wants the length of all 12, so that times that by 12, that'll give you 2.25 meters, which is obviously B. Alright, let's look at the next one. So number 2 is quite straightforward. You just need to know the electromagnetic spectrum, which you really should know from GCSE. So it would go radio waves, microwaves, infrared, visible, UV, X-ray, gamma, and so this is the long wavelength. Just do a quick overview. This one will be high wavelength. I might as well do a bit more. So in terms of frequency, gamma is high frequency, and radio waves are the opposite, low frequency. And then in terms of energy, obviously gamma rays are high energy side of the spectrum, and the radio waves are low energy. Then just check the question. So which gives the regions of the EM spectrum in order of increasing wavelength. So increasing wavelengths that direction. So in this instance, X-rays, UV, infrared, radio waves, in that order. So I'd probably just do a little sketch, like this on the side of the question, and then just pick the correct order. So the answer will be A. So let's look at number 3. The frequency of the first harmonic of a wire fixed at both ends is 300 hertz, and then we double the tension, and it wants to know what the new frequency will be. So the equation for this one is frequency is 1 over 2L square root T over mu, mu being the mass per unit length. Now the only thing that we actually need for this question is the relationship between the frequency and tension. So frequency is directly proportional to root T. Now if you're like me and don't like square roots, I would write that as frequency squared is proportional to the tension. Then we can do this question. So it says the tension is doubled. So if I double the tension, I need to multiply the left hand side, the frequency squared, by 2 as well, or make the entire thing 2 times greater. You might think, oh, I'll just put a 2 there, but you can't do that because that'd be 2 squared, which is 4. So you have to actually multiply it by root 2, because root 2 squared is 2. So on both sides now are 2 times greater. So the frequency, the original, the 300 hertz, will increase by a factor of root 2. So if you do that, put that in your calculator, you'll get 424 hertz. So the answer is C. Alright, let's look at number 4. So for this one, number 4, we need to come up with an arrangement that gives you the same fringe spacing. So for this one, really, you just need the equation. So it's what lambda equals WS over D. It's on data sheet. So the fringe spacing W is equal to lambda D over S. Then you just need to make sure that the numbers add together properly. Yeah. So in this instance, it's A. You can see by looking. So lambda is 2, so 2 times the wavelength 2. The distance is 2 times, and the spacing of the double slits is 4 times. So the top is 2 times 2 is 4. 4 divided by 4 is 1. So we're still at W. So A. Let's look at the next one. Yeah, this is a common one. So we've got monochromatic radiation wavelengths given, incident nonlinear diffraction grating, and it gives us the lines per meter. Now you've got to be careful of this because it can give you lines per millimeter, but this time's lines per meter. So the equation is d sine theta equals n lambda. So on this one, D is just do a quick reminder in case you don't know, when you've got your diffraction grating, you get like, lots and lots of lines with a really small space between them, and they're normally given, something like this. So we've got 3 times 10 to the 5 lines per meter, and D in the equation is the distance between 2 individual lines. So what we need to do is figure out D first. So I'll just make some room. Hopefully that's okay. Been reminded. So 3 times 10 to the 5. So we need to do a meter divided by that. So we've got 1 meter divided by the number of lines per meter. 3 times 10 to the 5. If you put that in your calculator, you get 3.3 recurring. 3.3 recurring times 10 to the minus 6 meters. So now we've got that. Now we can figure out the highest order produced. So another thing that we could talk about is when you've got your diffraction grating, the light typically you'd have an n equals 0. I'll just do this as neat as I can. You'd have an n equals 0 line. Then you might have n equals 1, n equals 2, n equals 3, whatever it may be. The maximum angle it could possibly come out at is 90 degrees. So our angle is 90, so it's sine 90, and sine 90, if you're not aware, if you put that in your calculator, sine 90 is 1. So I'll just get rid of this. That's 10 to the minus 6 meters. So then we just get d sine theta equals n lambda, so d sine of 90 is 1, so we're just left with d equals n lambda. We've got D, we've got the wavelength, we can rearrange to find N. So N is equal to D over the wavelength. So D we just calculated, 3.3 recurring times 10 to the minus 6, divided by the wavelength, which is given in the question, 5.8 times 10 to the minus 7. If you calculate that, and there's something else I want to share with you, and actually this works out pretty well. So this gives us 5.747, so just say 5.7. For n. Now what you might think is 5.7, oh that rounds to 6, so the answer is B. However, this is a bit of a strange one whereby, that rule doesn't apply. You can't round up, if you remember back to the image that we drew, you can't round up to something that doesn't exist, because on the diagram, you would end up, so if that's n equals 0, you'd end up with something out here. Physically doesn't exist, so we actually can't round up, so what we have to do is round down, even if it was 5.999, it's still 5. So the answer would be A. Hopefully that one went okay. Let's look at the next one. Right, so number 6, which characteristics of monochromatic light change when the light passes from air into glass? So this is just, it doesn't have to just be air from air into glass, it can be from any medium into any other medium. It could be glass into water, or air into water, or into oil, it really doesn't matter. The thing is that you should know is that the frequency never changes. like the frequency is always constant. So, you know, it's definitely not A or B. Well, it has to be C. But let me do a little explanation as well, so, or a way to think about it. So when... That worked quite well. Let's say when light comes in, so let's say the light ends up there, just draw a normal, at whatever angle it might come in at. The wave, imagine, I don't know, imagine you were a beam of light and you ran into something that's more dense. You know, it's kind of going to get squashed together. Or if you run into a wall, you'd kind of squash a little bit. Or if you crashed a car into a wall, the car's going to compress. So the wavelength's going to get shorter as it enters a more dense medium. So the wavelength changes, and it also, you know, you're also going to move slower in a more dense medium. So, you know, C is very apparent to me. Frequency is always the same, so don't fall for that one. Hopefully that's all right. Let's look at the next one then, number 7. So number 7 says, which is a description of the pattern produced when monochromatic light passes through a very narrow slit. So when light passes through a very narrow slit, you get D, you get a wide central maximum with narrower side fringes, but I'm just going to go into a bit more detail. So you can get a graph. I'll try and draw this neat. There we go. You can get a graph whereby you can do, now it's intensity against position on the screen. So when it's a single narrow slit, what you get is a peak. So you get a big intensity for the central fringe, and then you get less, maybe it's a bit less than that, less bright fringes afterwards that are, sorry, that's not the best, that are thinner. So by thinner I mean, so that has, say that has 2W for its width. The subsequent maxima that follow are just W. So they've got half the width, and then it reflects on the left hand side as well. Can you tell I didn't do art? So like that. Obviously that's not to scale because, you know, they don't look that different, but the central fringe is much more intense and has twice the width of the subsequent maxima. That's for a single slit. What I would do is ensure that you know the difference for a double slit, and in fact I might as well tell you what it is. So for the double slit, you can have the same graph, you know, so it's intensity against position. I'll just call it IP this time. For a double slit, you get the intensity doesn't drop off nearly as much, and the width of the maxima is the same, so it kind of might look like that. So the width of the maxima is hardly changing, and they're all, the central fringe is the brightest though, and they are all, you know, the width of the subsequent maxima is identical to the central fringe. So that's for a double slit, just in case you need to know that. Okay, hopefully that satisfied that. Let's look at the next question. Right, so number 8, the fundamental frequency F is the lowest frequency heard when a stretched string is vibrating. So what happens is the string is lightly touched 1/3 of the way along its length for what is the lowest frequency heard. So what we're doing is essentially changing the length. So you might have a string that's vibrating in its fundamental node that looks like that, and then if you kind of pinch it off there, you're kind of changing it so it's that. Alright, hopefully that makes sense. So the equation, frequency, is 1/2L, square root tension divided by mass per unit length, or mu. Now the tension and the mass per unit length will be constant, they'll be the same thing. So the only thing that we're really interested in is frequency and length. So frequency is, you know, inversely proportional to length. So it's touched 1/3 of its way along its length, so that'll be a third. And frequency and length are inversely proportional, so if you got 1/3 of the length, you get 3 times the frequency. So 8 will be D. Let's look at the next one. So for this one, number 9, So we've got, it's straightforward, we've got a diffraction grating, we've got a screen. And the question, what's the number of lines per millimetre on the diffraction grating? So from d sine theta equals n lambda, the first thing that we want to find is d. And then once we've got d, it's d being the distance between two individual lines on the grating. Once we've got d, then getting the number of lines per millimetre is relatively straightforward. So what we need to do, we need the wavelength, which we've got, it's given in the question. We need the order, which is the first order, so we've got that. We just need the angle. So some people that do this don't actually spot that you can just use trigonometry. So we've got the opposite and we've got the adjacent, so we can just use tan theta. So tan of the angle is equal to opposite over adjacent, so that'd be 0.3 divided by 1.5. So yeah, theta, so inverse tan of 0.3 over 1.5 is 11.3 degrees. So from that we can find out d. So d would be n lambda over sine theta. So n is, in fact I'll write it out, n lambda divided by sine theta. Then we can put the numbers in. So n equals 1, so the wavelength is simply 6.5 times 10 to the minus 7 divided by sine theta, so sine 11.3. Which gives us distance d of 3.32 times 10 to the minus 6 meters. So what some people might do is go straight for A and be like, well, yeah, I've got it. But that's, it's a significant distractor. So if I get rid of that, so number of lines per millimetre, so what we need to do is a millimetre divided by the distance between two individual lines. So 1 millimetre would be 1 times 10 to the minus 3 divided by the 3.32 times 10 to the minus 6. Which gives us 301. So it's 301 lines per millimetre. So that'd be C, 3 times 10 to the power 2. So let's do one more, last one. So on this one we've got 2 points on a progressive wave. Now a wave like this, from beginning to end, the phase difference of the full wave is 2 pi radians. That's for a full wave. So pi by 6 radians, and then so it's 2 points on the wave which are pi by 6 apart, which is a 1/12 of the wave, so they're pretty close together. And then it gives you the distance between the 2 points, 0.12 meters. So if you couldn't identify that pi by 6 radians was a 1/12 of the wave, you could just do 2 pi divided by pi over 6. Which will give you 12 times. So 12 of those fit into a full wave. So if we've got the distance between the 2 points being for the pi by 6, we can just do, to get the full length of the wave, or the wavelength, we can do the 0.12 meters times 12 lots of that, which will give us 1.44 meter wavelength. Now we've got wavelength, we've got the wave speed. So we could just use V equals F lambda and rearrange to get frequency. So frequency is the wave speed, which is 340, divided by the wave, which is 1.44 meters. If you put that in your calculator, you'll get 236 hertz. So the answer is A. Hopefully you found that exercise useful, and you might have picked a few things up. So if you liked it, give me a like. If you've got any questions, drop me a comment, and thanks for watching.